Now in our next video, let's go ahead and dive into another analysis that's a little more applied. It's something that maybe we could see ourselves doing in terms of an actual analysis using this data set. So here we have the Kaggle data page. There are different tabs here, code being one of them. And there's notebooks or Kaggle notebooks in here that people have created to analyze this data set for various purposes. I have, of course, created a few. The first one we just looked at in previous videos. There's two others that I want to cover, a couple looking at different questions we could ask with respect to the data sets. So one of the questions that people always ask is, okay, you have 2 buildings or 50 buildings or 100 buildings. How can you compare these buildings against each other? Of course, different buildings are going to use energy in different ways. And is it really fair to compare, let's say, a grocery store building with a large warehouse? Or is it okay to compare a small office building with a larger office building? So there's a notebook here called Comparing Energy of Different Building Types. It's an example analysis we're going to use to solidify our understanding of using the Pandas library for meter data in buildings. So if you click on this and go ahead and copy it into your Kaggle account, what you're going to see is just like this. And the gist of this notebook, as mentioned, is really the comparison of buildings and a step called normalizing energy data, energy consumption data in a way that we can compare different buildings of different types and learn Pandas also at the same time. We're going to look at different buildings from the Building Data Genome Project. Of course, the first thing we need to do is load our Pandas library. We're going to go ahead and load the electricity data. We're going to go ahead and set the index column to timestamp. We're going to parse those dates so we have a nice date time index to use. If we take a look at that, we're going to see that we have 1,578 columns in here. When you have this many columns, your .info function is not going to show all of them. It's just going to show the first and the last and give you a number. It's going to give you a number of the rows or entries, and it's going to tell you the time range of your date time index in this case. 211 megabytes. Yeah, that's a sizable data set, in fact. Not big data, but I would call it okay size data. Bigger than normal data, let's call it. If we take a look at the head, we're going to see that all of the different buildings have their own column. Each of the timestamps indicates a time during this 2-year period. And let's just for analysis sake to just look at one of the buildings. Let's look at this office building called Hannah from the site called Panther. Let's load that data. Let's take a look at just this individual building. You can see that it's very simple data frame timestamp once again in your column. If we look at the .info, we're going to see that there's 8,760 entries. We've truncated one whole year off, so we're only looking at the 2017 data itself. So when you analyze building meter data, you're going to start to learn pretty quickly. Not only are there 12 months in a year, 365 days in a year, there is 8,760 hours in a year. This just confirmation that we have a full year data set from midnight on January 1st up until 11 p.m. on New Year's Eve of 2017. You'll notice that in our .info function, we've got 8,748 non-null values, which means that we're missing a few points. We're missing about 12 points throughout the course of the data set, which is pretty normal in this case. And a much smaller data set, 136 kilobytes of data. Our one column itself is a float 64 data type, so we know that it is numerical with a decimal point. So let's take a look at that real quick. Let's do a dot plot real quick to see what we've got here for Office Hannah. It's pretty messy, pretty noisy, but you start to see some patterns. You can see a lot of volatility across the days. This is hourly data across a year. This looks quite normal actually for energy data from a building. You see some little areas here where there's less consumption, probably holiday periods. This is in fact a campus, a university campus site, and you can find out more about that site from the Nature Scientific Data publication that I mentioned in the first video. We want to look at this energy consumption. This is kilowatt hours for each of the hours in the data set. This building is fluctuating between 5 and 25 kilowatt hours. So it's not a huge building, most likely, a pretty reasonably sized building. So we want to look at how can we normalize this. The most common way of normalizing building energy data is according to floor area. And in this data set, we have a metadata file itself. We can load that file and we can take a look at what's inside. What's inside the metadata file is in the x-axis. Now the buildings have been converted from fields into observations. So these are each of the buildings. And then each of the columns are some metadata about that building, what type of space it is. Here you see the floor area, latitude, longitude, time zone, year built, occupants, Energy Star, et cetera, et cetera, et cetera. Not all of these columns has all the data. If we do .info, we can see that out of 1,636 meters, we've got some of the columns are fully covered, but a lot of them, especially for example, so there's only 5 buildings in this data set that have solar meters attached to them. You've got LEED ratings on 136 buildings. So there's quite a bit of diversity, more as compared to what you have from your time series data. Let's take a look at our building itself. We had a variable that we called building name, which we used to load the data set. We'll go ahead and load also in metadata using .loc to find the metadata of this particular building. Site Panther, it's an office building. It has a year built, it has time zone, latitude, longitude, and square meters, which we're interested, or square foot, which we're interested in using for normalization. We can actually pull out using another selection process, another bracketed selection process to pull out that square meter value, 375.1. So you can imagine using the square meter value, using the energy data, normalization should be quite easy. And if you thought that, you would definitely be right. If we look at our energy data again, all we need to do is to create a new data frame called office example normalized is simply take this office example we have here and simply divide by this number that we've extracted from the metadata file, which is 375. What that does is it's a vector operation which divides all the values in this office example normalized by that 375. What you end up with is an hourly normalized. This is kilowatt hours per meter square per hour. So quite small actually. What we probably care more about is an aggregation of this, which we can use .resample to do. In this case, we'll .resample across the month. We will make a sum of that. So we'll see how many kilowatt hours per meter square per month there is in this building. And we'll also do a bar plot for this. So we have a monthly data, we'll do bar plot, we'll have a figure size, give it a title, and this is what we end up with. In this particular building, you actually have kind of this pattern of more energy consumption in the summertime months here in the middle of the year versus the ends of the year. Normalization is really best served when analyzing multiple buildings because you want to use these normalized values to see how well different buildings compare against each other. So what we're going to do once again is we're going to pull out a certain data set. This time we're going to look at the Wolf data set again. We're going to pull out just the buildings from that data set. Here you can see that when we do that, we have 36 columns. So there's 36 buildings in this particular site. The timestamp, of course, and the column headings are the same. We can look at .info to see how much data we have in each of the columns. So we see a list of the columns. They're all float data types. We can see some of the columns have a little bit less data, maybe some gaps in there. We loaded that whole data set. We can look at the head of the metadata file. We can pull out just the metadata for the Wolf site. And we can also pull out a vector of the floor area and square meters of each of the Wolf buildings, which we can see here. So this is a little trickier to do normalization across. Before we just had a single building, we were dividing it by floor area. Now we have a data frame with a bunch of buildings as columns, and we have a Panda series of the floors that we want to do normalization. So in this case, what we have to do is use .div, which is a function which allows us to divide a data frame by a series. So what it's doing in each of the columns of this data frame is dividing each column by the subsequent value from this series. So if we execute that, we see that now you have normalized values across each of the columns according to the floor area in square meters of each of the buildings. we can see quickly that this is an info of that normalized data set. Not much has changed here in the number of values and things and its float types. The best reason to normalize the data is to actually compare it against other buildings. What we're going to do now is let's go ahead and plot our regular normalized data frame. We're going to sort the axis according to the column names. So axis equals 1 is the column names. We're going to pull out the last 10 columns, last 10 buildings. We're going to sum those across the whole data set. So we're going to get an annualized, we're going to get kilowatt hours per meter square per year, and we're going to plot that as a bar chart. So what you see here is a data visualization where we have like Office Haiti, Office Joanna, Rochelle, Marcella. These are all offices, or these are retail over here, that seem to be using a lot less energy than this public building, Norma. Norma seems to be, a huge consumer of electricity as compared to its peers. But if we look at the normalized data, on the other hand, what you're going to see very quickly is differences. So all of a sudden, Wolf Public Norma is not such a huge consumer because, in fact, its energy consumption per meter square is much lower actually than some of the others, and in line with those other low consumers that we saw before. Whereas Wolf Science Alfreda is a building that's using actually a massive amount of energy per square meter. This gives us the ability to understand the differences and the impact that floor area has on consumption and normalization that allows people to be able to compare buildings against each other. So is it really fair for us to compare a science building versus an office building? Probably not. That's why there's other means of normalization, and that's why you generally try to compare only buildings within the same use type. But there are other ways of normalizing data besides just floor area, which you can explore in other ways on your own if you'd like.